Hello everyone, welcome to another video of quantum field theory. In today's video, we'll be talking about virtual particles. Now there is a lot of misleading info on virtual particles online and confusing statements about virtual particles. So I want to make this video to sort of clarify the role of virtual particles in quantum field theory, which will probably help out with our understanding of virtual particles a bit, if all things go well. So let's begin. So virtual particles represent what's called the Feynman propagator in quantum field theory, and I've written the Feynman propagator right over here. This begs the question: what is the Feynman propagator, which will be the topic of today's video. Now we can solve the Feynman propagator by using the path integral formalism of quantum field theory, where we use what's called the generating functional Zj. But since we haven't covered the path integral for fields, we aren't going to use that method. Or we could also go through the nitty-gritty math, which uses the canonical quantization method, which will be the routes that we'll be using in today's video, since we've already learned it. So yeah, we are going to use the canonical method to evaluate the path integral, to evaluate the Feynman propagator. Also, here is the notation that we will be using. I don't like it, but most people use this notation, so let's use it for our video today. So now let's actually talk about what we learned in the last video briefly. We learned about what happens when our field acts on the vacuum state. When our field acts on the vacuum, we get one particle at 4 position x. Now, I feel like in my last video, I gave off the impression that when we have a field acting on the vacuum state, we get one particle at the 3 position x. But really, it's the 4 position x, which in other words is a particle at some location x at time t. That's what happens when we have our field as a function of the 4 position acting on the vacuum state. However, if you had a field that had an input that was a 3 position and acts on the vacuum state, then we would get a state that's at 3 position x. And of course, it's an approximate state, by the way. So hopefully that clarified some things there. So yeah, also we looked at taking the inner product of the state with itself. Well, actually, we talked about this over here. And we actually interpreted this inner product for the case where we had equal times. When we have equal times, that just corresponds to this amplitude right over here, which tells us the probability amplitude that the particle goes from x to x prime, or yeah, in some equal time t, which is what we talked more in depth about in our last video. But again, we can look at this propagator in a more general case, where we have t is not equal to t prime, or like t equals t prime, or like t doesn't have to be t prime, if that makes sense. That's this over here, and that tells us the probability amplitude that the particle goes from x t to x prime t prime. Note that before and after are not specified, which means that t prime could be greater than t, or t prime could be less than t. So it's kind of weird here how we are kind of like treating these states as having no sort of causal structure yet, but we will. So now we can consider different situations here. Again, this over here is called the propagator, and we can use this shorthand notation for it. So if we let t be greater than t prime, this tells us the probability amplitude that a particle at x in time t was at x prime at some earlier time t prime. It's kind of weird here because the final state is the earlier state. So it's kind of weird, but it's just telling us the probability amplitude that a particle that's right now at xt was at x prime t prime earlier in time. And we call this propagator over here the advanced propagator, which we will be talking about more shortly. We could also consider the case where t prime is greater than t. This case makes a bit more sense. It's the probability amplitude the particle at x in time t propagates to x prime in time t prime. That's where the term propagator comes from. It's telling us that we have a particle at x t, and then the particle goes to x prime at time t prime. So like it tells us like where it's going to be. So this tells us where the particle likely was. This tells us where the particle likely is going to be. And we call this propagator, we call that the retarded propagator. So the retarded propagator is this right over here that we just talked about. And we can actually represent the retarded propagator in terms of the like building block propagator, also called the elementary propagator, right? And we can use the Heaviside step function in order to model that. And this makes sense because remember that the Heaviside step function is defined as being 1 if x is greater than 0, and it's 0 if x is less than 0. So if we were to graph the Heaviside step function on a graph, like where else would we graph it? We would have something that looks like this. And then yeah. So here's x and here's y. And we see that for positive values we have 1, for negative values we have 0. So this function works because it's only non-zero for t prime is greater than t. And that's what we want to consider for the retarded propagator. Likewise, we have the advanced propagator that we saw earlier. It's for t is greater than t prime. We could again represent it as this, but so the Heaviside step function is a function of t minus t prime. And again, it tells us how the particle propagated in the past. There's also another propagator called the causal propagator, which is this over here. And it kind of tells us the difference between two propagators, and it kind of ensures that time makes sense in a way. So why are we considering this propagator? Well, because the elementary propagator for equal times doesn't vanish from when the distance is large. So remember from our last video, we were talking about the amplitude that a particle goes from x to x prime. And we talked about how it behaves like e to the minus mr. Now e to the minus mr at very high distances does not actually go to 0. It approaches 0, but it isn't actually equal to 0. This means that we can have an electron that's chilling in like one spot, maybe in your living room, and like it just instantly like pops into like New Jersey or something, assuming that you don't live in New Jersey. So, or like the other side of the galaxy, right? And we can't have an electron doing that, right? It doesn't really make any sense. If you have a space-time diagram, we have things called light cones. And if some event is outside the light cone, that means that something inside the light cone cannot influence that event until that event is at the light cone. So if an event is outside the light cone, they can't influence each other, but if an electron is outside your light cone, doesn't it make sense for it to like teleport to your light cone in an instant? Because that would kind of like break causality. Now, technically speaking, relativity does not forbid particles traveling faster than the light cone, technically speaking. But if we do consider those paths, we do get like paradoxes. So we don't really like causality not being taken seriously in the mathematics. So we use the causal propagator to solve this. And it resolves this because when we subtract the propagators together, the e to the minus mr terms cancel out, so we do get exactly 0 outside the light cone. But I don't really buy this solution fully because it doesn't change the fact that our actual propagator that we considered, this one over here, doesn't vanish outside of the light cone. So it feels very ad hoc. So I don't really fully buy the argument. So, but I just want to show you guys what the argument is. So we can talk about these things more in depth, but I'm just going to briefly skim it so we can go to virtual particles much more sooner. So now we can talk about the Feynman propagator. So the Feynman propagator is this right over here. And you might be wondering what this T thing over here is. This T is called the time ordering operator. And it's defined as follows. It's defined as giving us phi x t, phi x prime t prime, for t is greater than t prime. This is an x, by the way. And then it gives us phi t prime x prime times phi x t if t prime is greater than t. So basically, t is the larger one, and then the term that contains t goes in front. If t is the smaller one, then it goes in the back. That's what this time ordering operator is doing. And I guess might be wondering why we are interested in using a term that looks like this. And the answer is that we see this term appear very often in scattering. When we use what's called the Dyson series, we find out that for higher order terms in the Dyson series, you will see terms that look just like this. So for now, it's going to seem very unmotivating, but when we get into scattering, we'll start pulling the tools that we use in this video. So it's going to be very important in the future. So this term, let's kind of erase some things to make things a bit more organized. So the time ordering, or the Feynman propagator, right? It's just a time ordered product of the elementary propagator. So this thing is telling us, so the physical meaning, this is important, the meaning of a time ordered, or meaning of the Feynman propagator, basically. It tells us the probability that a particle goes from xt to x prime t prime if t prime is greater than t, and the probability that the particle goes from x prime t prime to xt if t is greater than t prime. Now this, again, might seem like a very odd thing, like who cares? Like it's telling us that a particle goes from x at time t, so you have at time t, from x to x prime at time t prime if t is the later time, and then likewise, so if t prime is the later time, and then likewise for t. So it's not really telling us something very interesting at first, but it's going to be interesting in the future once we get into scattering. But this is the actual meaning of the propagator. It's telling us an amplitude, a probability amplitude that a particle travels to some spot, basically, in some time t. So, how can we actually represent this propagator in a much more nicer fashion? Because we have a time-ordered operator over here, but we have to, how can we write this without the time-ordering operator t? And we can actually write it by using the Heaviside step function, by using the same procedure that we use for the retarded and for the advanced propagators. So, we can actually write the inner product of t phi t x phi t prime x prime. We can write that as the Heaviside function of t minus t prime. So here the t is going to be the larger one of phi t x phi t prime x prime plus phi of t prime minus t of phi t x and phi t prime x prime. Actually, I think it should be the reverse. Yeah. Phi t prime x prime times phi t x. So how does this give us the same thing that we have here? Remember that for if t prime is greater than t, the thing is flipped, right? And that's what's over here, it's flipped. And here we have t prime is greater than t, so that we can have a non-zero amplitude here. Likewise for this first term over here. So we can just write the Feynman propagator as this right over here. And again, it's telling us the probability that at time t, we have a particle at x and then propagates to x prime at time t prime, and then likewise for x prime. So here's a concrete example. Let's say that t was greater than t prime. That would make this term go to 0. That would make this equal 1. And then we'd have phi tx times phi t prime x prime. And that's exactly the same thing that we have right over here. So that's how the Feynman propagator just works in practice. Now it turns out that we can simplify this inside term quite a bit by actually writing out the Heaviside step function in terms of a complex integral. So let's do that now. Also, an important thing, this expression right over here, it's actually equal to this without the inner product. That's what t phi x times phi t prime x prime is equal to. If we were to add the inner product over here, we'd have to distribute it to each term right over here. So that's an important correction to note. If we did distribute that, we would have this right over here. We would just be distributing those inner products for each term, as you see over here. And that's what the time-ordered product of the fields is going to be equal to once it's sandwiched together with the thingamajigs. So to simplify this thing, we have to note that we can write out the step function in terms of a complex integral, or I don't know, I don't think it's technically called a complex integral, but like in terms of an integral of a complex function. Now you might be wondering, how do we get this integral over here? I'm not really sure, but I guess it's a cool fun fact. We can write the step function in terms of this integral over some variable called z. Z doesn't have any physical meaning, it's just some variable of integration. And yeah, by doing that, we can isolate the propagator into two parts. The first part, which is this over here, and the second part, which is this over here. I want to say in advance, what's going to follow might be a bit confusing. This is where quantum field theory starts getting hard. So if it doesn't make sense the first time around, it's fine. But it's going to be a bit of a learning curve for some people, which is totally fine. So let's commence. So the first part is this over here. Now what we can do here to solve this thing is we can move the step function to the front. And doing that, we have this over here. And this product should be sort of familiar. We looked at it in the last video for the cases of equal times, but now we are going to have separate times. And that gives us this over here. Again, we calculate this already for equal times. For separate times, it's the same thing, but just you have to consider the small aspect, which is just going to be the fact that we are going to have a term where we have t minus t prime. But here is what we get for this inner product that we calculated in the last video. And now we can expand the step function and the integral that we saw earlier to get to this over here. Now we can actually check for ourselves that this is the right inner product, because we can try expanding it out. So what we have is the integral over k of 2 pi cubed 2 omega k e to the minus I k mu x mu minus x mu prime. So we can call this over here some for vector y prime, with the risk of abusing notation. So we have over here e to the I k mu y prime, which can be expanded as e to the minus I times k naught y naught minus the minus the 3 momenta k times the 3 y thingamajig. I forgot what it's called. So that's going to be equal to e to the minus I k naught y naught times e to the I k 3k times 3y. Now to expand this out again, that's just going to be e to the minus I k naught times t minus t prime, because y naught, since y prime is x mu minus x mu prime, y naught is x naught minus x naught prime, which is just t minus t prime, and then times e to the I k dot y. And for equal times, which is what we considered in the last video, this is 0, so this whole thing is 1. And we have e to the I k y, which is e to the I k times x minus x prime. And that's exactly what we found in the last video for this exponential right over here. So that shows that this is the correct expression that we have found. So after doing that, we need to solve this integral over here. Well, we're not actually going to solve it in this video. We're going to simplify it. So what we can do first is we can kind of note that we can combine the 2 pi cubed with the 2 pi. Also, here, let me just actually do it first. Oh, also this integral for the momenta, it's over negative infinity to infinity, but we usually just don't write it out of laziness. Physicists tend to be lazy when writing their bounds when it's over infinity, but we're going to have I times the integral from minus infinity to infinity dz d3k over 2 pi cubed to omega k e to the, 1, I want to write my things a bit better. It should be a 3k over here. So now we have 1 over z plus I epsilon e to the minus I z t minus t prime times e to the minus I k mu x mu. If we can fit everything in by moving it over, that was going to work, minus x mu prime. Now you guys might be wondering what this epsilon is. It's just some constant. We could let it be 0 at the end, but let's keep it here for now. So now we have this over here. Now this might be confusing to you guys. Oftentimes in physics, when we have very long integrals, we want to combine the integral sign. So this over here just means that we are integrating over dz and d3k over the same bounds. If we had different bounds, we would not be able to do this. We'd instead have to have another integral added. But since we have the same bounds, we're allowed to just kind of smush them together. So we have this over here. We can do some simplifications. We can look at this term right over here. So we are looking at, if we're to like take this and like zoom in, we are looking at e to the minus iz times t minus t prime times e to the minus ik mu times x mu minus x mu prime. Alright, so what can we do here? Well, again, we want to expand this exponential term. So we're going to have e to the minus I k naught times t minus t prime times e to the I k 3 momenta and then 3 position minus 3 position prime. I hope that you guys can convince yourself why this is going to be equal to this expression right over here. Spoiler alert, because remember that the dot product of like A mu and B mu is going to be like A naught B naught minus AI BI, or the 3A, whatever notation that you're using. So that's why this is going to be positive for the second exponential right over here. So we can now just move this guy down over here. And we can say, oh, look, we have similar terms over here, so we can combine them, or we can factor them actually, e to the minus iz minus ik naught times t minus t prime e to the ik x minus x prime. We can factor out the minus I, gives us z plus k. And then we have t times t minus t prime e to the ik, 3 minus ik, x minus x prime. I hope that makes sense so far. All we're doing here is just algebra. We're not doing anything like physics right now. Just basic manipulations. So that gives us this over here. We just factored out the t minus t prime from this exponential. That's all we did there. So what can we do now? Well, we can plug this guy back into the integral. We found that this was just e to the minus iz plus k naught times t minus t prime e to the ik, 3 onto k, x minus x prime. So now what we're going to do, you're going to use a u sub technique. Let u be equal to z plus k naught. That means that du just equals dz. Doing that gives us. So doing that u sub helps simplify our integral a little bit. And this is where the actual weird part comes in, all right? It would be really nice if we could combine these terms somehow to get some exponential times raised to the minus I times some sort of 4 vector v and then x mu. But we can't really do that. Well, we could technically do that actually. If we define some new 4 vector, let's call it maybe u. Yeah, that's the basic notation. We can't call it that. Let's call it no, we'll call it u prime. Or sorry, u mu. Where u mu is just u and then the 3 amounts of k. We could combine these exponentials together to get kind of one big old exponential where we have e to the minus I u mu x mu. But the problem is that we are still integrating over d3k and then du. So it kind of gets confusing a bit. So we could define a 4 vector where we have u and then k vector, right? And this 4 vector is going to be kind of similar to the actual 4 momenta, which is k naught and the 3 vector k. Now this is where things get, I keep saying this is where things get weird, but this is where things like actually really get weird. We're going to pretend, just for funsies, all right, that u equals k naught, or not equals k naught, that should not be the word. We're going to replace k naught with u. That's what we're going to do. Because here we have that u is z plus k naught, right? And k naught, remember, is the square root of k squared plus m squared, where k is 3 momentum, right? And that's also equal to omega k, by the way, which is what's over here. So we are going to replace k naught, this k naught variable, with that u. But u is not going to be equal to k naught, or u is not going to be equal to the square root of k squared plus m squared, okay? Because remember that u is k naught plus z, And z could like literally be anything, right? Where it's written over minus infinity to infinity. So it's let me just actually show you guys what I'm actually doing. So if we replace k naught with u, that's going to give us, or sorry, not k naught with u. Really, we're replacing u with k naught. That's what I mean, with u with k naught. That's going to give us I times the integral from s infinity to infinity d4k. We have d4k because if this is going to act like dk naught, we're going to have d4k. So d4k over 2 pi cubed 2 omega k times 1 over k naught minus, we can't call this k naught anymore if we let u be k naught. So we're going to have to call it omega k. And this was already omega k, but in this case, k naught no longer equals omega k if we are replacing u, or if we're, I don't want to say replace, if we're just going to call u k naught. So we're going to have k naught minus omega k plus I epsilon. And to make it even more clear that omega k is the energy, we're going to call omega k, let's just call that ek, right? To make it even more clear that it's the energy that we are dealing with. Then plus I epsilon, and then times e to the minus I k naught t minus t prime. So this is why we are going to relabel the u, which is just some meaningless variable, with k naught. So this is making k naught a meaningless variable. So we are not assigning a meaning to u. So when I say that we are relabeling u with k naught, I'm not saying that we are going to go, oh, it turns out that u is equal to k naught, because u is not equal to k naught. Well, at least what k naught originally was. But now by saying that we are replacing u with k naught, we're saying that we are redefining k naught to not be k squared plus m squared. So this energy now is no longer equal to the E equals mc squared kind of thing. And we call this off shell when k naught is not equal to the square root of k squared plus m squared. So we can now actually combine these guys as e to the minus ik mu x mu. That's why we did that relabeling. So now we have, and this is equal to the first term for the Feynman propagator. And that's our answer. So that's where we kind of stop there. We kind of stop integrating there. So I want to kind of clarify what we've just done here. So what we've done is we went, okay, we made some variable u, where u is just z plus, was it plus k naught, right? So u is just z plus the square root of k squared plus m squared, right? And now what we did was we said, okay, let's pretend that this dummy variable u, I don't think it's really called dummy variable in this context, but let's pretend this like dummy variable u is going to be k naught. And let's label it as k naught. This means that this k naught has to be relabeled as well to like omega k, but since that was what it's equal to already, right? So if we change the u to k naught, you have to change the k naught to like something a bit more specific, like square root of k squared plus m squared, or ek or omega k, whichever one you wanted to choose. And basically, if we pretend, or if we exchange the 4 vector k mu, which is k naught k3 vector, if we exchange that to u 3 vector, that's going to allow us to combine these two together and combine these two together in an elegant way to just get this over here. But if we do that, we have to note that k naught no longer has the same meaning as what it previously once was, which was the energy, right? Or omega k. So k naught no longer, it's not that it just no longer equals the square root of k squared plus m squared. It just no longer has any meaning at all. Because again, Z was the variable that we were integrating with respect to, right? And we're just adding the energy to Z. So we just get some variable U that doesn't have any physical meaning of its own. So K naught, it's not really an energy. You'll hear some people say that the energy of the virtual particle is off shell. That's technically speaking wrong. It's the virtual particle doesn't have, there's no energy, isn't even a meaningful thing to describe the virtual particle with, because K naught doesn't represent the energy anymore. Some people say the energy is off shell, which I technically already said it's off shell, because 2 minutes earlier, right? What I mean is that K naught is not equal to the square root of K squared plus M squared. But K naught is not the energy. Remember, we are kind of pretending that it's the energy, but it's not really the energy. It's just a math trick that we are using to kind of simplify our integral. I've spent a bit more time on this particular segment because you're going to hear some people say some pretty wacky stuff about virtual particles, like it all boils down to misinterpretations. So now we have this for the first term in our propagator. And now we have to do the exact same thing, but for the second term, this right over here. So this is this for the second term. Again, we can do the same steps. You can just move the heaviside function in front of our sandwich to get this over here. And that's just going to be equal to theta t prime minus t times 1 t prime x prime 1 t x. This is similar to the, it's very similar to this right over here. In fact, it's the same thing, but we just swap the vector and the covector around. So we found that this was equal to this over here is equal to it prime x prime. No, it was equal to itx inner product with it prime x prime. But what we want to find out is the flopped version of that. And we know that from like vectors, whatever, when we flip-flop the thing, you have to conjugate it, right? In other words, A conjugate B conjugate is just B conjugate A. So when we flip-flop, we have to conjugate. So we can just reuse the same result. We can reuse the same result, but we just have to complex conjugate something. So all I have to do is to complex conjugate the exponential, which just gives us a plus instead of a minus, and that's it. And then again, we can use the same formula. This formula over here, that was for theta of t minus t prime. What we're interested in though now is t prime minus t. So all we have to do is just do t prime minus t and just swap these around. T prime minus t. And with this information, we can write the second part, this over here. We can just write it out as, so we get this right over here. So again, it's the exact same thing we had before, but instead of a minus sign, it's a plus. So what we can do here are the exact same steps as before. We can erase the physics down below, and we can just kind of combine these integrals together. And combining them together, we're integrating from minus infinity to infinity. We're gonna have d4k over, oops, sorry, we're not there yet. We're gonna have dz d3k 2 pi cubed 2 omega k, right? 1 over z plus I epsilon e to the minus I z t prime minus t e to the I k mu x mu minus x mu prime. Okay, so what to do now? So we're going to expand this out. This time we're going to have e to the I k naught t minus t prime times e to the minus I 3 vector x minus x prime, and then multiplying that by e to the minus I z t minus t prime minus t. But note for a second that here we have t prime minus t, and here we have t minus t prime. So we can't really combine them. Well, we could combine them, but let's do some smart stuff before we combine them. Let's distribute the negative sign in front. That's going to give us e to the iz t minus t prime. And now it's in the same order as this one. So since it's in the same order, it's going to be pretty straightforward on what to do to factor them. That's just going to give us e to the I z plus I k naught times t minus t prime e to the minus I k 3 vector k x minus x prime. We can factor out the I from there. You get z plus k naught t minus t prime e to the minus I k x minus x prime. Again, we can do the u sub. We can let u be z plus k naught. This means that dz equals du. And doing all of that, we are going to get. So we now have this over here. Now, if we scroll all the way back to what we were doing before, the 3 vector was positive, right? It was e to the positive number. But here, it's e to a negative number. So in order for us to combine the first term with the second term in a nice way, we want to make this term be e to the positive number. So to do that, what we can do is take the 4 vector, u and then k, to be, we're going to change it and to be minus u minus k. Is this valid? I don't really know why it's valid or if it's valid. The book I was using just kind of did that without any motivation. I see why it's doing that, so we can get this to be positive, but it doesn't really show if it changes our expression, or like why it doesn't change the expression. We just change u to be negative u and k to be negative k. Doing that, this over here, this bit over here, is going to be e to the minus iu t minus t prime, e to the I k x minus x prime. Now again, if we use the same trick where we let u, or we label k naught, sorry, we label u to be k naught, the same trick as before, we can then write this as e to the minus I k mu x mu. Sorry, did I say k mu x mu before? Okay, no, we are. Oh, that's a mistake. This should be e to the minus I k mu x mu minus x mu prime. I don't know why I wrote it like that. Yeah, we should have minus x mu prime. FYI, hopefully y'all spotted that on the first try. So yeah, we should have that right over there. Okay, so let's scroll down a bit. Okay, so we have e to the minus I k mu times x mu minus x mu prime. Realistically speaking, we are actually letting k naught, we're technically letting k naught go to minus k naught. So that makes this over here become a positive sign, because minus k naught is just positive k naught. But we're still taking this u over here, we're changing this u over here to be a negative number, because at first it was a positive number. Sorry, at first it was a negative number, and we're changing it to be a positive number because we are letting kind of u assume the role of k naught. So that's how we can kind of get away with changing this one and this one at the same time. So by doing that, we now have So again, what we did here was we kind of changed the u to being the k naught. That's us kind of letting u take the role of k naught. And we label k naught to being ek. Again, ek is the same thing as omega k, but ek is just a bit more obvious to be the energy. So now we can, of course, just remove the I over here. That will just give us, and this should actually be a negative sign in front. But the reason is that if we are changing k, basically the k vector, to be minus k mu, what happens to d3k? So we had d3k and then dz, right? So if we change k, or I guess 3k, the 3 vector k, to minus 3 vector k, we're going to have dk2, dk3, and then dz, and then minus dk1, minus dk2, minus dk3, and then dz. And these give us a negative sign in the front to get negative dk1, dk2, dk3, and then dz, or just minus d3k dz. And then when we let dz just be du, we have minus d3k du, and that'll just give us a minus d4k. So again, we're kind of doing like a bit of a sneak over here. We are letting u assume the role of k naught, but we're not going to change u to minus u directly. So we have this over here, and that's responsible for the negative term right over here. So that is our answer for the second term. Okay, for the second term. So what we had originally, the entire propagator, scroll all the way up, and we erase the irrelevant things, we have that it was equal to this. This was the Feynman propagator. And we wanted to find this first term and the second term. And for the first term, we found out that the value was equal to, for the second term, we found out that it was equal this over here. So all we really gotta do here is just add these guys together. So the inner product, you'll also hear this being called the 2-point correlation function. The inner product of these guys is just going to be equal to this first term minus the second term. And all we have to do is we can just factor out the common term. And also, we can combine this as this right over here if we were to kind of like distribute the 2ek. Because remember, this is times this entire thing. If we were to distribute the 2ek inside of here, actually, that's how we can get that e squared k term in there. So doing that, we now have that the Feynman propagator is going to be this over here. There should be no 2ek. It's going to be this right over here. And that is our answer. I've highlighted some things because we can note that the Fourier transform of this expression over here, the Fourier transform of that, is just going to be this right over here, which gives us delta. I'm just going to call it delta k. So a shorthand term for the Feynman propagator, you'll see it. Delta is a common way. You also see delta of x minus y. You might see df of x minus y. There's a bunch of different ways of symbolic ways of writing out the Feynman propagator. So what I've written it as here is delta of x mu minus x mu prime. I think it might have to actually be a downstairs mu, but I tend to forget whether it goes upstairs or downstairs. So the Fourier transform of that's why I've highlighted this in the yellow. Remember, that's just going to be everything else is a Fourier transform. of because we have the base, because what's in yellow are the basic building blocks of the Fourier transform. What's inside is going to be like the f of k, right? So the Fourier transform of its expression is pretty simple. It's just this over here. So yeah, that is the how we write out the Feynman propagator. That's what it's actually equal to. So yeah, so how do we actually interpret this whole thing? It tells us the probability that some particle goes from x at time t to x prime at that time t prime if t prime is greater than t, or the probability that we go from x prime t prime to x t if we have t is greater than t prime. So it tells us those two separate cases. So that's what the propagator, that's what it like literally means, the amplitude. That's like the actual meaning. Now, where do virtual particles come into this picture? Because you'll hear people say that, oh, some particles can pop in and out of existence, and that it's allowed because the Heisenberg uncertainty principle tells us that for small times, the energy is uncertain. So particles can sort of steal energy out of the vacuum as long as they give it up later in the future. And they'll tell you that that's what this propagator means. These particles pop into existence. Now, if you guys have been following close attention to in this entire video, you will see that in no way does it actually entail that. Nothing in the math and the interpretation, nothing in the direct meaning of what we've done so far says that particles can pop in and out of existence. Like, hopefully, if you guys haven't been exposed to that in the past, hopefully you're kind of scratching your heads right now and thinking about how people make that sort of jump in logic. Like, how do they even connect the two together? Because like this Feynman propagator, right? It represents the amplitude that of this occurring. What's inside of this rectangle over here. It doesn't mean it doesn't mean that we can have particles that pop into existence and things like that. So why do people say that particles pop into existence? Well, there are these things in quantum field theory called Feynman diagrams. So we can have an electron over here. We can have a muon over here. So here's the Feynman diagram for electron muon scattering. And this internal line and the squiggly line, the Feynman diagram, let me make it a bit more pretty. This squiggly line in the Feynman diagram, it's called a virtual particle. And this virtual particle is a symbolic representation of this propagator right over here, or this one, depending on whether you are Fourier transforming or not. Now, these diagrams that we draw here, these pictures, they represent terms in what's called the Dyson series. And what's important here, what really matters is that this internal line, this virtual particle, is just a symbolic representation of this propagator over here. Now, some people give a little bit too much meaning into these Feynman diagrams, and they start thinking that these diagrams represent an actual physical process occurring. And they'll start thinking that, oh, the electron and the muon annihilate, or no, sorry, in this case, the electron and these electrons exchange the virtual photon. They create a photon that comes from nothing, and the photon gets destroyed eventually at this point, and that causes the electrons to generate muons or whatever. But that's misinterpreting these Feynman diagrams, because remember, this internal wavy line over here, this virtual particle, represents this over here. It's not that this represents this, it's the other way around. These diagrams that we draw, they're just ways, they're very convenient ways of getting the terms in the Dyson series. We don't even have to ever use Feynman diagrams in quantum field theory. Like, we don't have to draw pictures. We could just evaluate each term ourselves, right? It's just that using Feynman diagrams, we get the answer faster. So that's why some people think that the propagator represents an actual physical particle, because in scattering theory, this wavy line over here kind of looks like it's a particle. It looks like we have an actual photon being emitted. But this wavy line isn't an actual particle. What it represents is a propagator. So actual particles, right, they are represented in the formalism of the Hilbert space. They are represented as Fock states, right? These are the Fock states. They're the Kets, right? In this case, we have the vacuum state, 0 particles. Uh, in this case, we have, what's a good example to use? In this case, we have one actual physical particle, but the propagator is not a particle. It's not a Fock state. The propagator represents an amplitude, right? Not an actual quantum state. I mean, quantum states themselves kind of also do represent amplitudes, but that's only when we actually take the inner product of those states together. So they tell us information about amplitudes, but the propagator itself isn't supposed to be, it's not representing a particle. So that's an important thing to know. So what about the Heisenberg uncertainty principle, right? You'll hear people say that, oh, because of this over here, this equation over here, I think it's less than or greater than, I don't know. It might be this sign, I can't remember, but I think it's this over here. They'll say that this equation over here tells you that we can steal energy as long as we get it back, and this implies the virtual particles. That's completely, absolutely wrong. Nothing in what we've covered, like, in our entire discussion, we haven't talked at all until now about the uncertainty principle. We didn't talk about Heisenberg's uncertainty principle to derive the propagator, right? So that tells you immediately that this explanation for virtual particles is wrong. And there's a difference between simplifications and misrepresentations. This is clearly a misrepresentation. The virtual particles aren't related directly to the Heisenberg uncertainty principle. Yet the energy of virtual particles isn't an actual physical meaningful energy, right? It's more of a demi-variable. What the virtual particle means, if you hear people say virtual particle, what they mean, it's just a short way, it's a short form way of saying the propagator. So what are virtual particles? They're the Feynman propagator. And where do they show up? In scattering. And we are going to be talking a lot about scattering when we read our scattering units. But yeah, that's what we have for now. So that's what virtual particles are. That's how they are represented in the mathematics. They are the mathematics, really, because virtual particles in the Feynman diagram, they represent the terms in the Dyson series. I'll talk about what the Dyson series is in the future when we get to scattering again, but that's just the reason why I'm including this part of the video is because some people might come in with misconceptions about virtual particles, so it's a good thing to respond to those misconceptions. So with that being said, that's the video for now. Thanks for watching and have a great day. Till next time.